So I've got a slightly more challenging problem involving verifying if a given function is a solution to a differential equation. And this is problem 21 from section 1.2 of the textbook that I'm using. So let's take a look at it. This is asking if the function phi of x equals x to the power of m, where m is any number, and this is why it's more challenging, is because they're not just giving us one function to check, they're giving us infinitely many functions to check in a way and asking us to find the function that works. Ask which values of m make this phi of x equals x to the m a valid solution to the differential equation 3x squared times the second derivative of y with respect to x plus 11x times dy dx, just the first derivative, and then minus 3y equals 0. Well, the first thing that stands out here is simply that we have this explicit function. And because the function is explicit, we know it's not implicit, so we're just going to try to find, all right, we already have phi of x, let's try to find phi prime of x, and then phi double prime. And we can just substitute it in, and hopefully we'll get some kind of algebraic expression, which we can then solve for m. Well, okay, the first step in all of that is to actually find the first and second derivative of phi, so let's find the first derivative. So phi prime of x. This is going to be just the power rule. M times x to the m minus 1, straight out of the power rule. Now, the second derivative, phi prime prime. This one is going to be very similar. We're just going to say we already have m, and now we're going to have to take down m minus 1, and then x is going to now be m minus 1, which is m minus 2. And, alright, that wasn't too bad. Now we have our first, second, and 0th derivative, I guess you could call it. We can go ahead and plug this all in. So, what do we get? We get 3x squared times the very first of our derivatives, so the double prime. And the double prime was, I'm going to distribute this, so m squared minus m, and this all times x to the m minus 2. Now we have plus 11x times the first derivative, which is just m times x to the power of m minus 1. And here we have minus 3 times, and now the 0th derivative, in a way, just the regular old function, is just x to the m. And this should equal 0. Now, let's do a little bit of simplification. We have some powers of x getting thrown around here, getting multiplied together. And what happens if we have, for example, x to the power of a times x to the power of b? This is going to equal x to the power of a plus b, right? Well, we can apply this rule of exponents to this here, because we have x to the power of 2 and x to the power of m minus 2, x to the power of 1 times x to the power of m minus 1. Well, what do we get? So let's try plugging it all in. We get 3 times x to the 2 plus, and now this one, 2 plus m minus 2. But as we can see here, these are just going to cancel out. And then we have, this is all times our old m squared minus m. I'm going to erase this because I think it's going to start getting in the way fairly soon. Alright, now we have plus 11 times x to the power of 1. There's a hidden 1 right here, x to the power of 1. But now we're multiplying it by x to the power of m minus 1. So we're going to multiply in here, or add, I suppose, because now we're doing it that way. Add in plus m minus 1. And then, of course, we can go about here and just multiply in by the m that we still had there. Finally, just minus 3 times, and then just on its own, technically we could say there was an x to the power of 0 here, but we'd just be adding 0. It wouldn't change anything. And this negative 3x to the m, we're adding that, and this is all meant to equal 0. Now let's rewrite things a little bit, and hopefully it's going to become clear what our next step should be. So we're going to have 3 times x, and I'm going to drop all the special colors now, because there isn't much to do with them. 3 times x to the m times m squared minus m plus 11 times x to the m, because this plus 1 and this minus 1, they cancel out. So 11x to the m times m minus 3 times x to the m. This should all equal 0. Well, what's become clear now is, well, hey, we have this x to the m term, well, coefficient, I should say, getting multiplied in to every term. Let's factor it out. Well, if we factor it out, we're going to get something that looks like this. X to the m times 3, and I'm just going to distribute this out, 3m squared minus 3m plus 11m minus 3. This all has to equal 0. Well, what is in here, and I wrote 11x. I meant to write 11m. The x power was extracted, factored out to the front. This is minus 3m plus 11m, not 11x. That was my mistake. Well, what we have on the outside is an exponent, right? X to the power of m. Well, if we know anything about exponents, it's that they never equal 0. The best that you can get out of them, let me draw a graph to make this clear, and let's try to do a slightly straighter x-axis. Okay, the best that you can get out of them is very close to 0. And then, of course, once you start hitting 1, they'll explode off to infinity. This is something of what an exponent might look like, right? As you go off to negative infinity, you'll get very close to 0, but you'll never actually equal 0. Now, the one exception to this is when the base x equals 0, but because this is a function spanning all values of x, that special case isn't going to really matter, because there's always going to be another case to override it and make the differential equation false. Well, if we have this exponent, it's never going to equal 0, and we have this multiplication, x to the m times this over here, one of these here has to equal 0 if the whole expression is to equal 0. Well, because x to the m is never going to equal 0, we can effectively get rid of it, stop considering it, because only this is going to matter. And now this is pretty exciting, because now we have this. Let's just simplify it out. 3m squared, and then minus 3m plus 11m, that's the same as plus 8m, minus 3, we have that this equals 0. And this is great for us. This is a quadratic in terms of m, that when we solve it, hopefully it's going to give us values of m that are valid to solve this differential equation. Well, let's go ahead and scroll down a bit, and it doesn't look like we're going to be able to factor this too easily, so let's just try plugging it into the quadratic equation. We're going to get that m is equal to, now let's do our different coefficients, so we're going to have a negative b, so negative 8, plus or minus the square root of, and now we have b squared, so 8 squared is 64, and then we're going to have minus 4 times ac, but we have a minus in the c anyway, so we're just going to make that be a plus. So plus 4 times a, which is 3, times c, which is 3. Well, 3 times 3 is 9, and 9 times 4 is 36. So we can say plus 36 on that end. And we're going to divide this all by 2 times a. A is 3, so 2 times a is 6. Well, this is looking up because we have a reasonable expression here in the square root. We have 64 plus 36 is going to be 70, 100. 64 plus 36 is 100. And what is the square root of 100? Well, it's 10, because 10 times 10 is 100. So we're going to have negative 8 plus or minus 10 all divided by 6. These are the possible values we're saying that m might be. So if we calculate this out, this means that m is going to be one of, perhaps, maybe negative 8 plus 10 is going to be 2 2/6. 2/6 is the same as 1/3. Or, perhaps, so we say, or m could be equal to, if we had subtracted, negative 8 minus 10 is negative 18, divided by 6 is negative 3. Well, these are the two values that we were able to calculate, and if we go back up, we remember, well, these were corresponding to the functions for 5x equals x to the power of m. So if we come back down here, what we're saying is that the solutions to the differential equation are equal to, there are two solutions, phi of x equals x to the power of 1/3, and another solution is phi of x equals x to the power of negative 3. That's these two are both solutions that will solve the differential equation 3x squared times the second derivative of y with respect to x plus 11x times dy dx minus 3 equals 0. We're saying that these are the two functions that will solve it that are in the form x to the power of m. And if you would care to verify this with the standard way, go ahead. It's going to be good practice. But that is all for this video. I will see you in the next one.